Hello, ladies and gentlemen. Thank you all for tuning in tonight to my show. And what we're going to talk about right now is amides. Now, the amide is one of the least reactive of the acid derivative structures. The amide itself looks like this. It is a carbonyl with a nitrogen over on one side of it. So, if it is a primary amide, it looks like this. 2 hydrogens on the nitrogen. A secondary amide looks like this. 1 hydrogen and 1 carbon on the nitrogen. And then finally, a tertiary amide is this. 2 carbon groups. Now, of the 3 of these, one of them actually shows some very interesting characteristics, and it's this one. So let's talk about why really quick before we get into silly little things like reactions and how we make. So for the amide here, this structure is actually crucial. Because what I want you to note here is that the carbonyl oxygen and the hydrogen on the nitrogen are parallel and opposite. That's actually very, very important for a reason I'm about to show you right now. More than any other of the acid derivatives, the amide lives in a constant state of resonance. And that resonance looks like this. New pi bond formed between the nitrogen and the carbon, breaking open the carbon-oxygen pi bond, and the other resonance form is this, where you end up with a negative charge on your oxygen and a positive charge on the nitrogen. Because a significant fraction of the amide structure is always switching back and forth between those two, that means that this bond here is non-rotating. Most of the other groups that we've seen, the acid, the ester, etc., that thing can spin like a top. Here it cannot, because you've got this hybrid between these 2 structures. And one of them, a very significant one of those structures, comes from the fact that that carbon-nitrogen pi bond prevents rotation. So that's why whenever you draw one of these amides, you need to draw them with, if it's a secondary amide, or a primary, it doesn't really matter because you got 2 hydrogens. A secondary amide, it matters because the hydrogen and the oxygen are pointing in opposite directions. Down here at the tertiary, not that crucial. Okay, so let's look at the formation of amides. You already know several ways to do this. For instance, one of them is the reaction of an acid chloride plus 2 ammonia molecules to give you the amide and a quaternary ammonium salt. The nitrogen is the best base in the system. You need 2 of them to get this done because one of them is going to be attached to the carbon. The other one will be the other one will be picking up the proton off of the product. This is the way most people make amides. This is actually the most efficient And honestly, about the only one that really works worth a damn. Anhydrides will do in a pinch. And we did this mechanism back with anhydrides earlier, so I won't bore you by frog marching you through it. You do need 2 ammonia molecules again. And you would get your amide plus the carboxylate salt plus the ammonium salt. In case you're wondering where that carboxylate salt came from, right there. All right. You can also, I suppose if you absolutely had to, you can make amides by reacting an ester plus 2 of the ammonias. And it will give you an amide, but no one does it that way because it is slower than molasses that you're trying to get on the winter solstice. All right, all that said and done, let's talk about the reactions of amides. So we've made our amide. And I want you to think about this for a second. If you remember that chart we gave at the very beginning of all of this, where we had the acid chloride, anhydride, ester, amide, and salt. We can form none of these molecules up above the amide from the amide. These cannot be made without first going back to the acid. The only 2 things that you can really make out of an amide is an acid or a salt, and there's one more I'm going to put in here because it doesn't really fit anywhere else, and that will be the nitrile. Nitriles really don't fit well into any other functional group family. At the family reunions, when all the functional groups get together, the nitrile has to sit at the weird, way out there picnic table and eat the iffy potato salad that's been out in the sun for too long. No one really quite knows what to do with the nitrile because, let's face it, it's part of the family, but it's a part no one really understands. Granddad, fought the Nazis, and when they liberated France, he got a little too excited, and then there's this whole branch of the family that nobody knew about. So, what we are going to focus on for the rest of this video is how we take an amide and we turn it into the acid and the salt. Subsequent videos will be about the nitrile. All right? So, I'm going to clear this page, and we're going to start by talking about amide to carboxylic acid. Okay? Amide to the carboxylic acid. Not shockingly, this is an acid or electrophilic pathway. Here's how the reaction works overall. And I'm just going to go with the primary amide here just because it's the easiest to work with. The amide in the presence of acid, water, and heat. And honestly, time. Amides are notoriously slow reactors. Will give you, not that. I was just seeing who was paying attention. Will give you the acid and the quaternary ammonium salt. Most of this process is reversible up until we get to the very end. Now, I don't have a lot of room here, so I'm going to skip over to the next slide before we start this. Here's the mechanism for this. Hopefully, by this point, some of you, if not all of you, are starting to understand that all of these reactions really do the same way. You just have slightly different functional groups all along. So here's our amide. The first step is the carbonyl oxygen deprotonating the hydronium. Equilibrium, and that puts you here. Your carbonyl oxygen is protonated. In comes our nucleophile of the day, which is water. Water will attack that carbon, open up the carbon-oxygen pi bond. Also reversible, which puts you here. All right, there's a positive charge on the oxygen from the water that we just put on. We're going to do an intermolecular proton transfer where the nitrogen grabs the proton off of the OH and the electrons stay behind to get rid of that positive charge on the oxygen. So now you're here. You've got this, that, and all of a sudden you've got ammonia there ready to go. That's a good leaving group. So guess what? It's going to leave. So now you're at this point with your acid. The ammonia is the best base in there. This is the non-reversible step that puts you at, I'm out of room, the carboxylic acid and the quaternary ammonium salt. This is the acid process. I'm not going to have time in this video to go through the base process, which is next. So what I would like you to do, I have like 2 minutes left before YouTube says you can't do this anymore. I want you to work on this mechanism. All right, at some point I quit recording, and it wasn't that long ago. So let's try this one more time. What you've got here is the amide. You react with sodium hydroxide, water, and heat, which will give you the salt and ammonia. Before you watch the next video, I would like you to please take a stab at this mechanism and see if you can figure out what it is. In the meantime, I'll see you hopefully in just a couple minutes when you have answered this and you're ready to go on to the next video.